we start with the energy storage TCP review of the last year, 2021. Teun Bokhoven will be the speaker. He is the chairman of the energy storage TCP. And Wim van Helden will follow. He is the task leader of task 39. And he will give us some highlights of this task. Okay, so with this, I open the stage for you, Teun.
Thank you very much, Stephanie. I'll need to share my screen. Okay. Well, good day to you all. My name is Teun Bokhoven. I'm currently the chair of the executive committee of the energy storage TCP, and it's a great pleasure for me to give some information and some backgrounds on what we do in the TCP, in particular in respect of what we've done in the past year, 2021. We have published our annual report on the website, but I would like to give you in the next 20-25 minutes an overview of the major issues we have been accomplishing in the past period. I split it up in three parts, but just, I don't know if all are, let's say, aware of the IEA technology collaboration program. So I'll give a brief update on that, then some general highlights, and I spend most of the time on the highlighting of the various tasks we do in our TCP. The IEA Energy Storage Technology Collaboration Program. It's a mouthful of words, and it has a lot of meanings. It is part of within the IEA. There's the technology and network, where something like 35 TCPs, technology collaboration programs, about all kinds of technologies are being organized. The energy storage TCP was established in 1979, so that's a long period ago that have been working on energy storage. Today, more than 21 countries are involved in our TCP, and more than 250 experts participate in the work of the various tasks we have. The major role is that we try to cooperate with all kinds of organizations and other TCPs. Of course, we work on the research projects on energy storage. We also like to promote the increased deployment of energy storages. I think the urgency is enormous at the moment, and I'll come back on that in a minute. And of course, we also need to give and convey some major messages to policymakers. Our main mission is to contribute to this energy transition from a fossil fuel-based energy system to a renewable energy-based system. And of course, energy storage is a technology which is enabling that transition. The scope of our TCP is we deal with heat and cold and electricity, so the thermal applications of storage and the electrical applications, both on a centralized and a decentralized way. We focus on storages to be compact, safe, reliable, and affordable. Those are the key words we like to keep in mind when we work on the energy storage topics. Our main activities are that we do joint research within the group of countries which are connected to our TCP. We actively try to disseminate the results, and we have a website for that. It's very important that we try to include the industry as well as the scientific community and the public sector in the work we currently do, because it is important to have all these factors together in this effort. And we look at the very integral approach. The energy system as a whole is basically the environment we have to position the energy storage in. So that's for us an important part, not only the technology development itself, but also how energy storage could fit into the wider perspective of an energy system. We do this by the way of tasks. We call this task, and each task is a specific topic, a subject, where researchers around the world are working together and collaborate to work on a specific topic. Typically, the task duration is about 2 to 4 years, and then we can continue, or if we have another subject we'll deal with. The research priorities we have is thermal storage, that both is for heat and cold. Now we deal with underground storage systems, but also TCMs and PCMs, and sensible heat and cold storages. Electrical storages, in particular with relation to the grid and the connection and the system aspects, also in buildings. Hybrid options like power to heat or power to gas, and those kind of intermediate options will be regarded, and we'll deal with modeling. Those are the major priorities we have in our work. So doing this work, we do this in tasks, and all these tasks we have basically divided in 3 categories: energy storage in energy systems, materials and components, and the technology development in itself and technology improvements. I will discuss these various tasks in the second part of the presentation. But first, some general highlights in 2021. I think everybody is aware that the sense of urgency to deploy energy storage is increasing tremendously. In the past year, we have seen very important and also alarming reports by the IPCC, but also by the IEA itself, which forecasts and predicts that we have at least a doubling of flexibility options required by 2040. So that is basically increasing the need for energy storage as part of the transformation process. We also recognize that there are many international organizations and initiatives who also are boosting the request and the implementation of energy storage, like the World Bank, Mission Innovation, and others. And all types of storages are therefore needed in terms of size, response time, capacity, and application area. So there's a wide range of storages which are needed. This is basically where we have to look at. The policy recommendations we have given in the past year are basically 2 levels. The economic ones is that we have, let's say, tried to emphasize that the economic value of energy storages are different from all kinds of applications and technologies. I give an example that if you look at how 1 kilowatt hour of battery capacity of a cell phone would cost approximately 10,000 euro if you calculate it back to 1 kilowatt hour. If you do the same kilowatt hour in a thermal variation for residential hot water, it will be €1 or $1. So it gives a wide variation of technologies and a wide variation of application areas, and therefore also a wide variation of cost and economic value. And this is an important factor because in the past, the value of storage has not been really taken into account with the system transformation going to renewable energy circumstances. So the value depends on how we can utilize energy storages in a total system concept, whether it be industry or in self-consumption in domestic applications, or in a wider range of the total energy grid. In all these aspects, energy storage will have a certain value, and it is better and good that we understand the values of that. So by gaining more recognition and awareness about the economic value, we see that there is far more interest from the science, from the political interest, and also economically on how we can use energy storage in our systems. With regard to policies, we have made very strong recommendations to policymakers that this economic value of storages need to also be implemented in government regulations. We are very much aware that the electricity grids are really stressed at this point in time through the growth of the sun and the solar and wind energy, but at the same time also the changing patterns with electricity consumption for electrical vehicles, for heating and cooling by electricity and heat pumps. That causes a lot of time differences between time of production and time of deployment and use, And that basically requires that there is a new set of government regulations required to allow energy storages to be integrated in the system, particularly in the infrastructure. The second message is that, of course, as we have an urgency to deploy more storages, there's also an urgency to provide enough funding for the research and demonstration and the deployment stages. That is a message we have to prevail and conveying to many of the governments. Successful international collaboration is also a key success factor if we want to increase the research activities from many of our activities within the TCP. On the communication side, we have, just for your reference, we had a very successful conference, INESTAR conference in Slovenia last year. We're participating in quite a number of workshops and conferences worldwide. And we have in our task meetings, approximately 25 task meetings was held in 2021 with the participation of more than 150 institutes and more than 250 experts globally. So that's a very strong and a wide community of experts we'd like to see in our ecosystem of our energy storage TCP. And last but not least, we have started 4 new task proposals and we'll highlight them in a minute. So going to this overview of all these tasks, I'll just briefly mention the main issues of these various tasks. To start with the energy storage and energy systems, we have a couple of tasks in that area. The one which is will be completed by March next year is a modeling task. A group of scientists are working on energy storage models to be implemented in the traditional simulation modeling we have, let's say, available in many forms, like you have the TIMES or TRANSIS or other models, simulation models, which have difficulty in determining the exact parameters of energy storage. So this task works on how we can contribute and provide through an open source method the right conditions and the right information based on a database to include that in these existing simulation models. We hope to have this as an open source models available by March 2023. We work very closely with the IEA itself. The IEA, of course, has make very strong predictions every year and outlooks, and they're very much keen and interested to include in a better way the storage parameters in their modeling. Further information, Professor Dr. Christian Dutsch from the Fraunhofer Institute in Germany is leading this task, and if you want any information through our website, you can be in contact with him. Another very important task, which is hopefully will be concluded at the end of this year, is the task on flexible sector coupling. It's a complicated issue, but we're very much aware that many people around the world are looking at how this sector coupling can be realized. And sector coupling in this mean that we basically looking at the production of renewable electricity and how that will be served and will serve to new areas like thermal applications in buildings and industry, hot and cold, but also to the change in the fuels for vehicles, for the mobility, to electrification. All these new forms of demand profiles from electricity based require that there is some sort of a intermediate gremium like storage to facilitate the use of all this electrons and energy. So flexible sector coupling is looking specifically at how energy storage can facilitate an easier transfer, an easier coupling of sectors like thermal applications, mobility, and electricity production. It has a very important impact on a lot of the system design aspects we see around the world. And it is an interesting topic. We'll probably have an end result by the end of this year. Further information can be received by Dr. Andreas Hauer from the Bavarian Center of Applied Energy Research, ZIE, in Germany. Another task in this energy storage and energy systems context is a smart design and control of energy storage systems with the basically a link to artificial intelligence for net zero energy buildings. The goal of this task is to investigate smart design and control strategies, in particular with energy storage, in trying to optimize the balance between supply, domestically produced renewable energy, and the demand sides in buildings. It will be providing information on guidelines and for operations and some more general aspects of artificial intelligence in controlling these strategies, controlling these new systems. Oops. And I'm sorry. And that will be completed by May 2023. The information, this task is led by Professor Dr. Ryozo Oka from the Institute of International Industrial Science in Tokyo, Japan. And it is a very interesting, more scientifically oriented task where we have more insight on how artificial intelligence can be contributing to control strategies and storage. Task 39. This is a task which will be highlighted by the next speaker, Wim van Helden. So I won't give a lot of time for this because he will in detail tell you about this task. It deals with large thermal energy storages for basically for district heating. Very important in the transformation. And I think very, particularly in Europe, we now see a huge, let's say, pressure to get alternatives for natural gas. And these kind of systems with district heating and large-scale thermal storages are extremely important to find solutions for the short term already. But Wim van Helden, who is the operating agent for this task, will tell you there in a few minutes. The last task in this section this technology improvement part, which is a bit different, is what we call the confident climate box, which is a kind of a strange wording, a strange name for an integrated concept of heat pumps, energy storage, and a control system. Basically bringing this in a kind of a box concept, its integrated version as a unit. It can provide the heating and cooling on site, and particularly for the building sector, and it can be fed by renewable energies. The most important part of it is that it will give some freedom in time of use and time of production from renewables back to the energy form you like to see in your domestic application. So it has an importance for grid stability, and it is kind of a project which has a stronger impact because it could be and should be scalable to larger volumes. The initiative for this project came through Mission Innovation, and we work very closely together with the heat pump TCP, and basically the project has been finished by a few months ago, and we'll have the report available in the autumn. It's an interesting concept, and try to most likely it will have a follow-up to make it more let's say affordable, cheaper, but the concept itself has been proven and is an interesting way to scale up the use of energy storage in combination with heat pumps for a large market in both heating and cold applications. The other task on technology improvements deals with Carnot batteries. They're inexpensive and site-independent storage ways of electricity, and the task has generated a lot of interest internationally because there's a lot of developments and also a lot of unknown information. So this task has been able to provide a good overview of the state of the art of the R&D for Carnot batteries. It deepens the understanding for what it basically can be done, what their role could be in the future energy systems, and how they could be let's say, scaled up and deployed in an even larger scale. The results provide a better understanding of the technology, and it will be disseminated about that. We have seen that a lot of interest now already is leading to follow-up activities on this task. It's very interesting, and I surely can recommend that you will follow the developments. The expected end date of this task is to end of 2022. And for further information, you can connect to Professor Annelies van der Sikkel from the German Aerospace Center, DLR, in Germany. The final one in this technology improvement block is task 38, which deals with ground source de-icing and snow melting systems for infrastructure. You have to consider it will be bridges, runways for Air Force, airstrips, where currently there's kind of electrical resistant heaters used to de-ice these kind of structures and infrastructures. And this task deals with how we can use geothermal energy or ground source heat pump systems for this de-icing activities. It's an interesting, of course, it's a niche market, but there is a very considerable amount of CO2 reduction to be achieved if you can transform that from electrical resistance to more renewable sources. The expected end date will be July 2024. The task is led by Bijan Al-Zourabi from Chalmers University in Technology in Sweden, and Aziel Sitin from the Turkish Society of Heating, Ventilation, and Air Conditioning in Turkey. Well, to conclude this round of tasks, we have one which on materials and components. This is a continuing task which we have for many years active now, and it deals with how the research on how to develop and create compact thermal energy storage materials. Focus will be is there on PCM, phase change materials, and thermochemical material developments there. Try to categorize them, and we keep a database on the most promising material developments in combination with the heat exchange capacity and also with the reactors to be used in with these various materials. It's a very important work as the compact thermal energy storage materials will have an enormous promise. If we have factors of, we have reduction in factors from compared to traditional water, for instance, it has a huge impact on the deployment possibilities of thermal energy storages. The expected end date of this task is June 2024. We do this in collaboration with the IEA Solar Heating and Cooling, TCP, and further information can be acquired by Andreas Hauer from ZIA in Germany, and also Wim van Helden, who will be the next speaker anyway. So these are the ongoing tasks. It's 8 tasks where a lot of people are working together, and we try to, of course, create a pipeline of new activities. Being selective, what is the important areas to focus on? So in 2021, we have started the development of 4 new tasks. One will be on techno-economic assessment for thermal energy storage, which is called Eco-Enesto. It's a new task which will be starting somewhere in this year, where we have we'll make an economic analysis for the further deployment of energy storages. So I mentioned in the beginning the need for an economic value of energy storage. This task will provide information how this could be evaluated. Then there is a new idea for the standardized use of building mass as storage, in particular for to create some more grid flexibility. It's a theme which comes up with the stress in the basically in the electricity grids, and it's the storage through the building mass can help relieve the stress in the infrastructure, and that is work in progress now to develop a task for that area. The third one will deal with energy islands, including energy storage. Well, it will assess the role of energy storage if we consider a hub function of large-scale renewable energy production, for instance, through wind and solar, and the various demands profiles we can achieve. And these hub functions with energy storage can, again, have a great impact on the electricity infrastructure. And on the technology improvements, we'll start a new task this year in 2022, where we lay the basis in 2021 on large-scale medium duration energy storage, which will deal with the intermediate term. So not minutes or seconds like the flywheel developments or the seasonal storage. It is the intermediate period of time where we seek solutions, scalable solutions for electricity storage for that area. And this task also will start in the course of this year. Well, more information you can find on our website. There's a newsletter you can sign up for. And of course, this annual report you can find on our website as well. Feel free to check it, and hope you can be in touch and be part of our ecosystem in the future and help us achieving the very important goal of more energy storage in our energy system. Thank you very much.
Thank you very much for the talk. It's always, I think, nice to see how much work is there combined together and how many different international groups and scientists are working in this and so on. Yes, so do we have any questions? In case you have, just give a sign or write in the chat. Okay. So I might take the chance and ask something if there's nothing. Maybe there will be a question rising up for someone. Now, considering the fact that many things are lately changing in the energy system, maybe in the long-term plannings of some countries and the energy demand. So, is there anything going directly from government or politics, so some direct connection between the task work and government, or is this like one step in between, or like a specific questions or something?
Well, of course, what we try to do in the executive committee, where we look at subjects of the task, is try to be as closely to where the major needs are. Of course, there's a lot of research being done, but we try to focus on where the research and the collective effort we have with all the participating countries in our TCP, how that could bring the technology further. So we hope that we can encourage people in their various institutes and universities and companies who work on the storage issues by working together on a specific issue in a task. They can progress faster and try to find solutions on a better way. So that's something we like to achieve and prioritize. And of course, the current geopolitical situation is even pushing us harder and make it more urgent. Similar with the climate change discussion, I think the urgency now is higher than ever. So it gives a pressure on us to deliver and seek the international collaboration as much as possible.
Yes. Yeah, thanks for answering. Yeah, I think it's good to be well connected. Yeah. So if there's no other question, I think we can proceed to the second speaker. Thanks again, Teun, and welcome, Wim. So please, the stage is yours. You can share your screen.
Thank you, Stephanie. I'll open the presentation. It should be full screen now. Is it okay?
Yes, perfect.
Perfect. Thanks for the introduction. As already introduced shortly by Teun, the task 39 is on large thermal energy storage for district heating. And as the title says, it has as aim to work on the technologies and materials and the policies that enable a further and quicker introduction of these kind of thermal energy storage systems into district heating systems. The first question is why at all should we have large thermal energy storages for district heating? This is because we all have a target for 100% renewable energy generation in the near or further future, at least before 2050. And these large thermal energy storages, they provide more flexibility in these district heating systems, enabling them to have a higher share of renewables and waste heat, or geothermal, for instance, and also enable peak shaving or power to heat, meaning that sector coupling will also be enabled by these thermal energy storages. And there is a large variation in operational conditions on short term, on long term, on middle to very large district heating systems. And this is all being provided or compensated for by large thermal energy storages. So they are needed to serve larger district heating systems and other large applications. That is also why in the subtitle it's also referring to industrial heating systems. And they are also needed to further reduce the specific costs. So the goal of our task 39 is to determine those aspects that are important in the several phases, namely the planning, the design, the decision-making, and the realization of very large thermal energy storages in order to integrate them properly into district heating and industrial processes. We have broken down this main goal into different objectives that will be reflected in the different subtasks that we have in task 39. The first is to define a number of representative application scenarios and to work on the boundary conditions for these scenarios and on key performance indicators. The other objective is to improve large thermal energy storage materials and materials performance measurement methods. So specifically on key materials being needed for those storages. The third objective is to prepare guidelines to obtain proper water quality. We have seen from practical examples that water quality is very important, especially for the tank thermal energy storage and the pit thermal energy storage. On the fourth place is to compare the performance and accuracy of the simulation models for large thermal energy storages, and connected to that to derive validation tests for these simulation models. And last but not least, the idea or the objective is to generate information packages and to disseminate these information packages to targeted groups, among those also the decision makers. What is the scope of our work? We look into 4 different kinds of large thermal energy storage. It's the tanks, it's the pit, the borehole, and the aquifer thermal energy storage, meaning that either water or soil is the medium in which the energy is stored. And we look at volumes typically larger than 50,000 cubic meters for district heating or industry. And we look at seasonal storage, but also at daily storage or multifunctional storage. And the dissemination is targeted to decision makers, either in policy or in municipalities or utilities or district heating companies. So those people that are in charge of those systems that would profit from large thermal energy storage. We subdivided the work into 4 subtasks. You will see the subtasks more in detail later. One on application, Subtask B on the components and its materials database, the Subtask C, which is the biggest subtask on the round-robin simulation, and then Subtask D on the knowledge base for decision makers. There are several connections, input-output connections between the different tasks. And the idea is that all the work in the first 3 tasks lead to information that is being gathered by the 4th task and being prepared for dissemination to the decision makers. We have 11 countries participating in the task. They are listed here with the institutes and organizations that provide the experts working in the task. So we have 33 organizations from these 11 countries, and these are subdivided into 13 industry or platforms and 18 R&D. And I see that this doesn't sum up to 33, so I made a miscalculation in it, but you can find out yourself where the two others are. Let's go through the subtasks. The first one is on the application scenarios, the assessment of the concepts and integration aspects. It's led by Pierre Delmas from UHeat, a company that is working on integrating and designing thermal energy storage to implement them, integrate them into district heating systems. The goal of this task is to define a number of representative application scenarios, to also define the connected boundary conditions in order to give people an idea of what the critical aspects are of the design of these systems, and key performance indicators, giving possibility to have a say a basis for comparison between the different technological solutions. So what we did is we drafted a list of system level and storage level key performance indicators. On a system level, this is, for instance, the CO2 savings provided by coupling the storage into the system, and primary energy savings. And on storage level itself, the number of cycles per year that can typically be provided by the storage, its efficiency, the thermal losses, and the specific storage capacity costs. And on the site-specific indicator level, it's the geological conditions and legal aspects, mainly connected to the groundwater legislation. Here's an example of part of the drafted key performance indicator table. First, a group of district heating network related key performance indicators, like the increase of the renewable share or the reduction of fossil fuel dependency on the district heating network. Then there are some storage related KPIs, as examples here, the storage capacity in megawatt hours, but also the storage capacity related to the site. So in specific in megawatt hours per cubic meter. And third group is the economics. So the least cost of the levelized cost of heat. And for instance, the storage volume cost, so the euros per cubic meter, or the storage capacity cost in euro per megawatt hour capacity. This is only one part of the KPI table. It's being refined with the present work. And at the end, we will have a KPI table that experts can use to make a fair comparison between the storage technologies on different levels. On the Subtask B, materials and components, we work on improving LTES materials and materials performance measurement methods, and to prepare guidelines for obtaining the proper water quality. It's led by Bijan Adel-Zarabi from the Chalmers University in Sweden. And what we worked on now is that material characteristics and performance data are gathered and will be included in the already present database, which is the SuperGen storage database from the University of Birmingham, which is now mainly dedicated to electricity storage, but will now be completed with materials data from thermal energy storage for large thermal energy storage systems. Other work that is being done is to specify the desired functionality of materials needed for large thermal energy storage. And one example here is to decide what the functionality is of different layers of a floating cover for a pit thermal energy storage. This is done by Aalborg CSP, a company from Denmark, designing and realizing these large thermal energy pit storages. You see here, for instance, that on the bottom layer, there is a barrier that has as function to make sure that there's no hot water and no moisture diffusion into the top layers of insulation. Then the thermal insulation has functionality to provide thermal insulation, but also should resist the weight from the top, and eventually also some moisture that could leak from the bottom. And then there's the top layer, a ballast, which defines the weight pressure, and all these layers in between will have a functionality that is determined by these characteristics. The idea is that different other components from the different other systems also will be approached by this functionality schemes. In Task B, we also work on corrosion-related water quality requirements. And also for tank and for pit thermal energy storages, there are some metal components in the storage that will corrode under influence of one factor is the oxygen contained in the water, and the other factor is the chloride content in the water. And the upper table is for large amounts of oxygen, so more than 0.02 milligram per liter. And the bottom one is for lower contents of oxygen. And the red areas are those areas that we should move away from. And only the green and yellow areas are the areas that are suited for applying metal components into such a storage. And you see that for large oxygen content, it's very critical that there is a typical pH value, and also the chloride content should be low, while for low oxygen content, there is a less critical area with a larger variation of possible pH, so the acidity of the system, and also a larger possible variation of the chloride content. So in practice, the water being used in these kinds of systems has to be prepared in order to have either a low oxygen content or with a higher oxygen content, a certain pH amount. And this helps designers of these kind of systems to make sure that the lifetime is also the expected lifetime. Going to subtask C, the round robin simulation. Thomas Schmidt from Solitest, Germany, is leading this largest subtask. Its goals are to compare the performance and accuracy of the simulation models for these kind of storages, and also to derive validation tests for the simulation models. So the different models will be targeted at different test sizes. There will also be defined the inlet and outlet temperatures. We have defined also which kind of round robins there will be taken. A round robin is, say, a concerted action in which different experts work with different simulation models to solve a similar problem. So there will be some reference cases, and there will be some targeted numerical simulations of storages. And this will be done by different experts on different numerical modeling programming software. And then they will be compared and see what can be improved, either in the software or in the procedures defining the boundary conditions for the different cases. So there are two stages. The first stage is that there will be simple operation of the storage. So 3 months charging, then 3 months rest, and then 3 months discharging. And there will be done multiple storage cycles. Then after this simple operation results, a comparison will be made. And after the comparison, then eventually some adaptations, possible adaptations, a seasonal storage operation will be performed, also with multiple storage cycles. There's also discussion ongoing on the challenges in the simulation model. For instance, how to work with thermal bridges between the lid of the thermal storage and the wall of the pit thermal energy storage. Example is here for this problem solving. Normally it's the cover insulation has a certain thickness, and there's heat leaking from the side of the water through the soil to the top, to the ambient. Normally, the cover insulation is numerically solved as only a very thin layer that has a certain resistance, and therefore the thermal bridge here will not be properly calculated. And in practice, there are two possible solutions to solve it: to have the same cover thermal resistance, but have an overlap, so a small overlap. And then there is a similar thermal loss, but there's the wrong ground temperature at the surface here, at this top red point. And the other approach is to have a cover insulation as an adapted thermal resistant and soil layer. So it looks like a soil layer that's on top of the storage. Then there will be correct top thermal losses and also correct ground temperatures, but it's more numerical solution work for that. And this is one of the discussions ongoing between the experts, how to solve this problem in practice between the comparison of the different numerical models. Also, a choice has been made for the different geometries that will be used for the round robins. There is 2 tank thermal energy storage configurations, one underground and one above ground. There will be one configuration for a pit thermal energy storage, a configuration for a borehole thermal energy storage, and for an aquifer thermal energy storage. So in effect, there will be 5 geometries calculated by the experts on the different numerical simulation software. Then Subtask D, the knowledge base for decision makers. It's led by Geoffrey Gauthier from Plan Energy in Denmark. The goal here is generally to generate information packages and to disseminate this to decision makers. What we already did is we designed and sent around an online questionnaire for decision makers. There were 54 reactions up to now, and we made the first analysis. There are, to our surprise, the reactions showed that 24 large thermal energy storages, mainly in Europe, are already in planning or in realization, which is a larger number than we had in our knowledge. The other result is that system perspective, key performance indicators and technical aspects and financial aspects are seen as most interesting for the decision makers. To our surprise, project feasibility and the planning was not seen as interesting, which in practice by the experts is shown that actually in practice, when realizing a project, this is very important, meaning that we need to focus with this dissemination also to the aspects of project feasibility and planning. So that's one of the, or a few of the outcomes from the questionnaire. 54 experts or people responded to the questionnaire. The largest group came from utilities, energy company, 15 persons. Then 13 persons came from academia. The third group with 7 came from manufacturers, meaning that we have at least most of the participants coming from the utilities and energy companies, meaning that we have targeted already a group that we see as the target group. The questionnaire is still open, so if you are interested in participating in this, please send me an email and I then can forward you the link to that. We still are working on the task. There are semi-annual task meetings. We had the first in-person meeting in Austria after 1.5 years virtual meetings. This was in April. And the next is planned in Denmark, in Aalborg, on 15th and 16th of September, which will be connected or after the energy systems, Smart Energy Systems Conference, which will be in the same place 3 days before. If you are interested in participating, it's open for the participation. Please contact me or your national delegate from the IEA Energy Storage TCP. The list of this can be seen on the website. Thank you for your attendance and looking forward to your questions.
Many thanks, Wim. Thanks for the talk, and I hope you maybe won some participants for the survey.
Hope so. Yes.
Yes. I don't know if is there any question, any hand raise? 1 second. Okay, not in the moment. Well, so I just take the chance to ask if I understood something right. Maybe we
Yes.
have some questions later. About I think it was the part C about the round robin test. Did I get it right? So there are different scenarios and different people with different software, probably homemade or commercial, and it will be compared to field data, or is it just around the software as first?
We try to gain as much as possible field data. There are some data available from Danish with thermal energy storage, and we are looking for more data, especially also for aquifer and oral thermal energy storage. And the idea is, yes, in the second round, so there's 2 stages. The one stage will be more artificial, just charging 3 months, then 3 months storage, and then discharging 3 months, in order to have this simple case as a first comparison. And then the second round preferably will be with actual data. Okay,
very cool. I think this is a very interesting step. The simulations always have to be taken carefully, I think. So it's good to have a good comparison. Very nice.
Yeah, the idea is then also to have a sort of choice table at the end of the task, giving people the choice to choose for which practical situation you could use best which software simulation model.
Very good. Very interesting. I'm curious about the results.
Me too.
Yes. Yeah. Okay, so now is the last chance for questions, if there are. Doesn't look like it, so maybe then people can ask you directly per email or so on if there's something not clear. And I just will now take the chance to share the screen. So just for your information, the next OnSeminar would be in August, but then we have a summer break, and we continue on the 27th of September. This is not a very fixed date in the moment, so still the topic is in discussion. But as soon as it's fixed, there will be an email, and it will be in the email distributor. You will receive the exact date and the topic as well. So this is not so much detail now, but just remember in August is a summer break. And yeah, with this information, I want to finish for today. Teun and Wim, many thanks for your talks. It was a very nice overview and a very nice review of the highlights. And yeah, with this, I finish for today, and I wish you all a nice summer break.